Okay, so today I'm going to talk about, this is going to be the second talk in the series, in the introductory series into the symmetric spaces of non-compact type. So last week, Juanma talked about just the basics of symmetric spaces and symmetric spaces of non-compact type, and also the Iwasawa decomposition and the Cartan decomposition. And this time I'm going to talk more about the restricted root space decomposition, which was introduced last week, and then also talk about roots and Dynkin diagrams. So, okay, just yeah, here's the plan. So first I'm going to kind of make a bridge between non-compact symmetric spaces and non-compact semisimple algebras. Then I'm going to talk about in more detail about the restricted root space decomposition. Then I'm going to give you an abundance of examples, and then we'll discuss the classification of non-compact symmetric spaces through the lens of the Dynkin diagrams and the restricted root spaces, restricted root systems. And then in the last part, it'll talk a bit about the Weyl group. So basically the entirety of the talk is just based on Knapp's book, Lie groups beyond introduction, and then also some parts I took from the book Submanifolds and Holonomy. More references are in Juanma's abstract from last week. Okay, so yeah, here's the bridge. So there is a one-to-one correspondence between the following things. Between irreducible symmetric spaces of non-compact type up to renormalization of the metric. So you're allowed to multiply the metric by a positive constant. Simple non-compact Lie groups. And here by simple, I mean not just topologically simple, which would mean that any normal subgroup is discrete, but like group theoretically simple. So there are no non-trivial non-compact, there are no non-trivial normal subgroups whatsoever. And real simple non-compact Lie algebras, where a Lie algebra is called compact if the Lie algebra of some compact Lie group. In other words, non-compact means that its killing form is not negative definite, but somehow semi-definite. Okay, and this correspondence is given by, if you give me a space, I give you the identity component with the isometry group. This will be a simple non-compact Lie group in the irreducible case. And to a Lie group, I assign its Lie algebra. Sorry, Louis, can you turn your mic down just because I hear some noises? Thanks. Yeah. So moreover, you can easily extend this by taking products in each of these three situations to a one-to-one correspondence between symmetric spaces of non-compact type, but now you're allowed to renormalize the metric by a positive constant on each Durham factor, and this constant might be different on different Durham factors. In the second case, you have centerless semi-simple Lie groups without compact normal subgroups. So basically, those are products of simple non-compact Lie groups. And finally, real semi-simple Lie algebras without compact ideals, basically just products of simple non-compact Lie algebras. Or not products, sums, whatever. Here's a warning that so the gist of this is that I can talk about non-compact symmetric spaces, or equivalently, I can talk about, say, real semi-simple Lie algebras without compact ideals. This is kind of a one-to-one correspondence. If you give me a real semi-simple Lie algebra without compact ideals, then I can recover the corresponding symmetric space by taking a simply connected semi-simple Lie group with this Lie algebra, taking its maximal compact subgroup, and taking the quotient and endow it with any G-invariant metric. So this is basically the bulk of the talk is going to be just purely about Lie algebras and real semi-simple Lie algebras in the non-compact setting. Okay, so the warning goes that it doesn't work for the compact type for many reasons. One reason, the main reason, is that you can have different non-isometric symmetric spaces of compact type that share the same isometry Lie algebra. So, for example, all Grassmannians of K-planes in Rn, they share the same isometry Lie algebra SON, regardless of K. So you cannot it's the correspondence that from a symmetric space gives you its isometry Lie algebra is not kind of injective in the compact type. Moreover, there are more subtle things, like, for example, you can have, if you take the I0 M for M of compact type, it may not be simple. It can have some non-trivial center, and there are more subtle things. But the main problem is that it's not a one-to-one correspondence anymore. So this is the feature of non-compact type. Okay. So let's start. So we start with a symmetric space of non-compact type. I want to allow to have representations which are not effective, slightly not effective. So I start with a Riemannian symmetric pair of non-compact type. So G, K, and then this involutive automorphism theta. And I denote by O the base point, which is the EK. And then I have G, the Lie algebra of G, K, the Lie algebra of K, and then theta is the induced involutive automorphism, small theta, of G. So here again, G is a connected semisimple Lie group. I'm just repeating what we had last week. Big theta is an involutive automorphism of G, pretty much by definition. Now K is precisely the fixed point set of theta. It's a connected closed subgroup of G. And theta, small theta, is the Cartan involution on G. This is pretty much the definition of non-compact type. So I decompose G into the Cartan decomposition, so the +1 and -1 eigenspaces of small theta, and call it K plus P. Now the Killing form B, that's the definition of Cartan involution, is negative definite on K and positive definite on P. And now what I allow, I assume that the action of G on M is almost effective. So the subgroup of elements that act trivially is maybe non-zero, but it's non-trivial, but it's finite. This is because mostly if you have a representation of a symmetric space, say of a semi-simple symmetric space, it's not the numerator is not the isometry group, but some finite covering of it. So that's why we have to allow this. And in this case, one can show that the subgroup of elements that act trivially is precisely the center of G, and also that this center lies actually in K, in the isotropy. And as Juanma mentioned last week, K is a maximal compact subgroup of G in this case. So, and one small thing which was also mentioned last week is that the isometry, the connected component of the isometry Lie group of M is covered by G. So every element in so kind of for a non-compact type or for a compact type, this representation by Riemannian symmetric pair is maybe not unique, but essentially you get every isometry in the identity component of the isometry group as coming from G. So G quotient out by this ineffectiveness, the center, is precisely the identity component of the isometry group. And finally, again, it was mentioned last time, M is a Hadamard manifold, so it has non-positive sectional curvatures, and it's simply connected. And in particular, it's diffeomorphic, but never isometric, to Rn. Okay, let's go next. So now we endow our G with a K-invariant metric, K-invariant inner product, B theta, given by this formula. It coincides with the Killing form on P, and is positive definite there. But it's minus the Killing form on K, and K and P, the summands of the Cartan decomposition, are mutually orthogonal with respect to this inner product. And now we make this standard agreement, which was mentioned last time as well, that the Riemannian metric at O, which is an inner product on TOM, coincides with the restriction of this B theta to P. So P and TOM are identified, and we agree that the Riemannian metric is not just absolutely arbitrary, but it comes from this inner product. This is a standard assumption. Now, the adjoint of X, if X is in the P summand, is a symmetric or self-adjoint operator on G, which we'll use in a second, as again in the reminder about the restricted root space decomposition. So we pick a maximal abelian subspace, A in P, and its dimension is precisely the rank of M. This is one of the definitions of the rank. Now, K, what I want to stress is that K, with the adjoint action, it acts transitively on the set of such maximal abelian subspaces in P. This fact was alluded to, or maybe like explicitly mentioned in the first talk about polar actions in December, because basically this can be interpreted as the fact that all sections of a polar actions can be obtained from one another by group action. So the choice of A doesn't matter. That's the idea. Now, for every element of A star, we define G alpha. It's the subspace of vectors on which vectors from A act just by multiplication by a constant, and this constant is the value of our functional alpha on this H in A. This is pretty much the same as you do in the roots theory of complex semisimple algebras. And with delta, I denote those alphas, non-zero alphas, for which this G alpha is non-zero. So elements of delta are called restricted roots, and the corresponding subspaces G alpha are called restricted root subspaces. Now, the word restricted comes from the fact that if you take the complexification of G, this will be a complex semisimple algebra. You can pick there naturally to construct from A Cartan subspace, Cartan subalgebra, and restricted roots can be obtained by taking roots in this complexification and restricting them as functionals to A. So that's why they're restricted. Okay, here are the main properties. Most of them were proved last time. So this is the restricted root space decomposition, is that G kind of decomposes as G0, and then this restricted root subspace is G alphas, and this is a vector space decomposition. Now, the summands of the decomposition behave nicely with respect to the lead bracket. We can describe G0 as composed of two parts, A, and then there is something in K. And this something in K, which we denote by K0, is precisely the subspace of K that centralizes A. Now, for any alpha, our involution theta maps G alpha onto G minus alpha. And also what's important, all summands of the restricted root space decomposition, so all G alphas and G0 are pairwise orthogonal with respect to our fixed inner product. And finally, delta is a root system, which means that, let me remind you that it spans A star, that if you take any root I will always omit the word restricted and just say root if there is no ambiguity. If you take any root and take the reflection of A star in the orthogonal complement to this root, this map will preserve the root system. And finally, if you take any two roots alpha and beta and project alpha onto beta, onto the line spanned by beta, this will be either an integer multiple of beta or a half integer multiple of beta. These are the three axioms of the root system. Okay. So yeah, and the inner product on A star is just induced from A. So one is immediate, and this was again discussed last time, because the adjoint of A consists of pairwise commuting diagonalizable, because they're self-adjoint operators. 2, 3, and 4 were proven last time. The proof of 6 is essentially the same as in the complex semi-simple case. I'm not going to give it here, but it's literally identical. And for 5, again, as in the semi-simple, in the complex semi-simple case, you can show that G alpha and G beta are orthogonal with respect to the Keeling form B, unless alpha is just minus beta. But now our inner product is not the Keeling form, but we kind of adjusted it to B theta. So b theta of g alpha and g beta is by definition the same as minus b of g alpha and then theta of g beta. But now we use 4. Theta of g beta is just g minus beta. So we have this, and now b is just the killing form. So this is 0 unless alpha is just beta. So which is exactly what we want in 5. All right, any questions here? All right, let's move on. So now we want to fix the subset of positive root. And again, I have to remind all this because otherwise it would be too abrupt to just start from some point of the last talk. So we fix the subset of positive roots, and there are 2 equivalent ways to do it. One may be more geometrically intuitive. You take a linear hyperplane in A star containing no roots. It's easy to do because the root system is just a finite subset of A star. And you declare all roots lying on one side of L, or any side, it doesn't matter which side you take, to be positive, and on the other side to be negative. Alternatively, and slightly more sophisticatedly, you pick a Weyl chamber, which is you take A star, you take all possible hyperplanes, which are orthogonal complements of the roots. You remove all these finitely many hyperplanes. The remaining part will be some open dense subset of A star, consisting of several connected components. You just pick one connected component. This is called a Weyl chamber of a root system. And you declare a root to be positive if its scalar product with some or any vector in this fixed Weyl chamber is positive. And you declare it to be negative if this scalar product is negative. Okay, so there is this notion. Basically, you decompose your root system into two equal parts. One is positive roots and the other is negative roots. And now you call a root simple if it cannot be expressed as a sum of 2. You call a positive root simple if it cannot be expressed as a sum of 2 other positive roots. And you denote the subset of simple roots by lambda, big lambda. Now I want to stress again that this choice of positive roots does not matter. For this, I need to make the following observation. If you consider K, and then you consider the subgroup of K whose adjoint action on the Lie algebra G normalizes A, then this group NKA naturally acts on A, and therefore on A star. Because you take K in this normalizer, you take its adjoint action, you restrict it to A, and then you take the dual operator on A star. And then you also, for good measure, put -1 in there in order to make it a left action, not a right action. So this gives you an actual representation of this normalizer NKA on A star. We'll need it later on. So the fact is that this, and we'll substantiate it later on. The fact is that this normalizer acts transitively on the set of Weyl chambers in delta. So if you pick any other subset of positive roots, then your subset of positive roots differs from my subset of positive roots by some normalizer of A in K, and therefore these choices are equivalent. So again, neither choosing A nor choosing the subset of positive roots matters. It's all equivalent. Okay. So now the main properties. Lambda is a basis for A star, and any positive root is a non-negative integer combination of simple roots. Then N, which is just the sum of all restricted root subspaces corresponding to positive restricted roots, is an nilpotent Lie subalgebra. This was also mentioned last time. Then the Lie bracket of A plus N with itself is N. So A plus N is a solvable Lie subalgebra of G. And finally, you have this Iwasawa decomposition, and here's pretty much the last moment where I need to recap on last week's talk. It's that J as a vector space decomposition is K plus A plus N. Okay, for the proof, one is just standard root system theory. Two follows from the fact that the Lie bracket of G alpha and G beta lies in G alpha plus beta, and the sum of two positive roots is positive. And 3 and 4 were discussed last time. And here is the picture. So it might be easier to think geometrically, schematically of G as the following. So you have this A, you have positive roots on one side of it, and then negative roots on the other side of it, and then you have this K0 box. Now, because I denote the positive roots, the sum of all positive root subspaces as n, then the negative ones will be theta n, or I can alternatively denote them as n plus and n minus, but people usually denote the above as n, so I have to denote the bottom as theta n. Any questions here? All right, let's go. So given alpha in a given root, I define the following two things. I define K alpha is the intersection. So I take G alpha, I take G minus alpha, I take their sum, and I intersect this with K. In other words, I take all possible vectors of the form x plus theta x, where x is in G alpha. And for P alpha, I do the same. I intersect P with this sum, and this will be of the form x minus theta x, where x minus theta x, where x is in G alpha. I'll give you a picture in a second. So this G alpha plus minus G alpha is the same as K alpha, plus P alpha. And why we're doing this is because we want to basically connect the Cartan decomposition with the restricted root space decomposition. So we want to express K and P in terms of this alphas and G alphas. So K is K0, and then the sum of all possible K alphas for alpha positive. And P is A plus the sum of all possible P alphas for alpha positive roots. So that's how they relate. And then there goes a picture. So you have this G alpha and G minus alpha, and in the space, in the subspace spanned by them, you can alternatively diagonally define this K alpha and P alpha. The two green lines generate this sum, but also the two red lines generate this sum as well. Okay, so that's how they relate to each other, the restricted root space decomposition and the Cartan decomposition. And now here's the main issue. There are two major distinctions between restricted root systems on one hand and the root systems of complex semisimple algebras on the other hand. And these two distinctions are, first of all, that our root system may be non-reduced, which means that if you have alpha a root, 2 alpha might also be a root. This doesn't happen in the complex semisimple case. And the second thing, that the dimensions of restricted root spaces don't have to be equal to 1. Remember that in the complex semisimple case, all root subspaces have complex dimension 1. Here, these guys may have real dimension greater than 1. So this dimension is called the multiplicity of alpha. So here you have this additional notion of multiplicities, which is kind of a vacuous notion in the complex case. And luckily, this delta may be non-reduced. Luckily, the root system theory tells us that there is only one non-reduced irreducible root system of rank R for each positive R. It's usually denoted as BCR, and it can be given like this. So you have the union of these three sets in R. The name is BCR because you can see that BCR contains BR and CR root systems as its subsystem. So BR is, I think, the smaller one. I may be mistaken. So you have to take this set and then the set of all two EIs. This will be BR, and one of them. So you take this first set in the union and then the second set in the union, And then their union will be BR, and then you take the first and the third, and this will be CR, I think. So you have BR and CR as subsystems, and their union is the whole BCR, hence the name. And the picture, here are a couple of pictures. So on the right, you have the BC2 root system. You can see that there is the B2 system is a smaller square, and the B and C2 system is this bigger square turned by 45 degrees. And you can also draw the Dynkin diagram of BCR. It looks like this. So here, there is one simple root whose double is also a root, and we denote it with these two circles with the same center. So it's the vertex on the right. So this is the root system. This is the Dynkin diagram. So now I want to give you a couple of examples of non-compact symmetric spaces and what their root systems look like. Does anyone have any questions at the moment? Okay. So first of all, hyperbolic spaces. So you take F to be either reals, complex numbers, quaternions, or the octonions, and you consider the hyperbolic space of dimension n over F. Here I require n to be at least 2, and in the case of octonions, n is precisely 2 because there is the Kelly hyperbolic plane, but there does not exist the Kelly hyperbolic space of dimension 3 or larger. So these spaces exhaust the list of rank 1 symmetric spaces of non-compact type. This is a standard fact. And the picture is as follows. So you have, again, this picture. You have A, which is just R because the rank is 1. You have K0 box in here. And then you have, because the rank is 1, you just have your root system is just either A1 or BC1. You have, if F is R, then you only have 2 circles. This circle here, which is just Rn minus 1, it's of dimension n minus 1. And you have the negative root subspace here, it's also Rn minus 1. If F is CH or O, then the root system is BC1, and you have this 2 alpha root, and its dimension is the dimension of your base F, so of your algebra F, minus 1. So in case of complex numbers, this G2 alpha is of dimension 1. In case of quaternions, it is of dimension 3, and in case of Kelly numbers, it's of dimension 7. So basically, you can think of this as you have Fn minus 1 here, and then you have another copy of F split into 2 parts. Its center, which is R, which is just A, and then the imaginary part of your real division algebra, which is ImF, and it's this G2 alpha. In total, you have Fn minus 1 here and another F here. And the K0 can be described like this. So here you have different, you can compute that K0 has these forms dependent on F and the dimension. Okay, let's move on. Now we have the split real forms. So G is called the split real form, or to be more precise, the split real form of its complexification, GC, which is also a semisimple, complex semisimple algebra, if the following equivalent conditions are satisfied. So A is a maximal abelian subspace of G. So we took it to be a maximal abelian subspace of P. So this is a stronger notion if it's maximal abelian in G. The second one is that the complexification of A is a Cartan subalgebra in the complexification of G. The third one is that K0 is trivial. And the fourth one is that all roots have multiplicity 1. So all G alphas are of real dimension 1, are just real lines. In this case, the restricted root space decomposition looks particularly simple. Let me go back to the picture. That's a long way. Yeah, so in this picture, in the split real form, you don't have the K0 box. So you just have this like block here and two pyramids on top and on the bottom. And also each circle is of dimension 1. Each G alpha is of dimension 1, so it's particularly simple. Okay, let me go back. Okay. And now the key fact here is that each complex semisimple Lie algebra admits a unique split real form up to an automorphism. I think up to an inner automorphism, but I haven't really checked. So the split real forms of classical complex simple Lie algebras are SL R plus 1R for SL R plus 1C. Actually, let me not like name them all. I've just listed them here. Note that there is a difference between the split real forms for SO over C, depending on whether it's even or odd. This is because the root systems for SO and C are different. They're either BR or DR, depending on the parity. Okay, and you can do the same for exceptional Lie algebras, but it's not really insightful because there's kind of like a bunch of notations. Here you can actually describe the split real forms in other terms. Okay. And finally, another example is complex semisimple Lie algebras. So let me actually start from something else. So you have symmetric spaces of compact type, and they split into two classes. One class is simple up to coverings is simple compact Lie groups and their quotients by their maximal property subgroups. And the other one is how to get a symmetric space of compact type. You take a compact semisimple Lie group, you endow it with a bi-invariant metric, and it will be a symmetric space of non-compact type. Such spaces are called spaces of type 1, traditionally. Their duals, their non-compact duals, are of the form G of C over G, where here you have G, a compact semisimple Lie group. GC is its so-called complexification, and then you take the quotient. These are called spaces of type 3. So this is how you describe this in the realm of non-compact symmetric spaces. But you can also give it a description in terms of the corresponding non-compact semisimple Lie algebras. Because the corresponding real semisimple Lie algebras are nothing but complex semisimple Lie algebras regarded as real ones, where you forget about the complex structure. So here it's also, you have the following. So you have G, a complex semisimple Lie algebra. You regard it as a real semisimple Lie algebra. And you have the restricted root space decomposition of GR of the realification. Basically, I just forget the complex structure. Kind of agrees with the root space decomposition of G regarded as a complex Lie algebra. Agrees in the following way. So you have these two blocks A and K0. And K0 is just A multiplied by I, where I is my complex structure in my Lie algebra. And A plus K0, which you remember is just G0, is actually a Cartan subalgebra of G, where G here is regarded as a complex Lie algebra. Okay. Now, my delta, which is a restricted root system for G regarded as a real Lie algebra, is nothing but the root system of G regarded as a complex semisimple Lie algebra with respect to the Cartan subalgebra G0. So basically the root system for G regarded as a real algebra and for G regarded as a complex algebra, they coincide. And the third one is that the root subspaces coincide as well. So G alphas are precisely the root subspaces of G with respect to the Cartan subalgebra G0. But now remember that in the complex case, each root space has dimension 1 over C, which is the same as 2 over R. So if my real semisimple Lie algebra is actually complex, then its restricted root space decomposition looks nice because the multiplicity of all roots are 2, so the dimensions of all restricted root subspaces are 2. And K0 and A are mapped into each other by multiplication by I. Okay? And the list of corresponding symmetric space of non-compact type is this. You have this for series for 3 series, but then the middle one actually splits into 2 depending on the parity of n. This is the classical ones, and you also have the exceptional ones. Any questions so far? So the main idea here is that, well, apart from the my first example was about hyperbolic spaces, but then for the other 2 examples are basically that for each complex semisimple algebra, you get always 2 real semisimple algebras. The first one is the split real form, and the second one is the complex semisimple algebra itself regarded as a real semisimple algebra. And now we'll see why this is important. So unfortunately, as we have already seen for hyperbolic spaces, the root system delta alone does not recover the symmetric space M. So remember that in the for complex semisimple algebras, you can recover the entire algebra by just the root data and basically by its Dynkin diagram. Here it's no longer the case, because you remember for complex hyperbolic spaces, or for quaternionic hyperbolic spaces of any dimension, or for the Cayley hyperbolic plane, the root system is just BC1, regardless of which space we take. However, the kind of information that is also there is the multiplicities of the roots. And so let me introduce the following definition. Let DDM stand for the Dynkin diagram of my restricted root system delta. And apart from looking at it as a graph, I assign to each vertex of my Dynkin diagram the multiplicity of the corresponding simple root. So now I treat my Dynkin diagram not just as a graph with some edges oriented or doubled or tripled, but as a vertex weighted graph. So each vertex in my graph has some number assigned to it. And as a vertex weighted graph, the Dynkin diagram fully recovers my symmetric space of non-compact type M up to renormalization of the metric on each Durham factor. Again, we can do the same thing. We can multiply on each Durham factor the metric by some positive constant. Okay, so you have kind of this combinatorial description of all symmetric space of non-compact type. Any questions here? All right, let's go next. So now let's look at the classification of symmetric space of non-compact type through the lens of their Dynkin diagrams and weighted Dynkin diagrams. Here's a nice example. Non-compact symmetric spaces whose of type dr, meaning that their root system is dr. Here is the Dynkin diagram. Here are these simple roots. And there are only 2, for each r, there are only 2 spaces with this Dynkin diagram. They're both written here, and this string of numbers in the parentheses is the multiplicities of the simple roots. So the numbers assigned to these vertices of this graph. Okay, now I claim that we know both of these spaces, because your complex semisimple algebra with the root system dr is nothing but SO to RC. And as we discussed, there are always 2 real semisimple algebras coming from it. One is its split form, SORR, and the corresponding symmetric space of non-compact type is here in the first row. And because it's a split form, all multiplicities are 1. And the second one is SO2RC itself, regarded as a real semisimple algebra. And the corresponding symmetric space of non-compact type is just SO2RC quotient by SO2R. And because this is a complex, algebra, the multiplicities, almost multiplicities are 2, because they're 1 over C, therefore 2 over R. We also discussed this before. Okay, and now it turns out that there are no more real semisimple algebras whose restricted root system is dr. So it's very nice. You have this 2 examples which are always there, and it turns out that there's nothing else in this case. And the nice part is that the same is true for E6, E7, E8, and G2 for pretty much almost all exceptional root systems, apart from F4. Now, the bad news is that it's no longer the case for other root systems, for AR, BR, CR, F4, and I mean, you also have BCR, which is kind of a has a separate place in the shelf. So let's take AR, the simplest possible root system. Its Dynkin diagram is just this. Now you have, these are the spaces with the root system with the restricted root system AR. So let's look at this list for a second. The first 2 spaces we already know. The first one, so your complex Lie algebra of type AR is just SL R plus 1 C. It has a split real form, SL R plus 1 R, whose corresponding symmetric space of non-compact type is written here, with almost multiplicities 1. And then you can also treat SLR plus 1C as a real semisimple Lie algebra, as a real simple Lie algebra in its own right. And then the corresponding symmetric space of non-compact type is here in the second line, and all multiplicities are 2. Now, there is one more, depending on parity, real form of the Lie algebra, SLR plus 1C. It's SLR plus 1H, where you basically quaternion R plus 1 by R plus 1 matrices with real trace 0. This is a real form of SL2R plus 2C. So if your R plus 1 is even, there is this real form, and it gives another symmetric space of non-compact type written here in the third line, with all multiplicities 4. But the problem is that there are no more non-compact real forms of SLR plus 1C. You can prove it. Yet, there are 2 more spaces here, which means that there are 2 more real simple Lie algebras whose restricted root system is AR and whose complexification is not even SLR plus 1C. One of them comes from some real form of the E6 complex Lie algebra, and the other one is nothing else but the real hyperbolic space, regarded as a symmetric space of non-compact type. Okay, so sometimes parts of it are nice, but sometimes for some root systems you have this weird simple Lie algebras, or in other words, symmetric space of non-compact type, which are kind of don't fit into the picture. Any questions here? Okay, we're almost done. So in the remaining 5 minutes, we just discussed the Weyl group. So again, what's the picture? We started with symmetric space of non-compact type. We said that they are basically the same as non-compact simple or semisimple real Lie algebras. For them, we kind of constructed this theory of restricted root spaces and restricted roots and restricted root systems. And for them, we constructed their Dynkin diagrams, weighted Dynkin diagrams. Okay, so now for every root system, there is a corresponding Weyl group. You can also describe this Weyl group in terms of the corresponding symmetric space of non-compact type and its isometries. So this is what I'm going to do in the last 5 minutes. So remember that we mentioned earlier, when we said that the choice of positive roots didn't matter, we said our reason was that the normalizer NKA acts transitively on the Weyl chambers. But remember that it's a standard fact from the theory of root systems that so does the Weyl group. The Weyl group of a root system acts simply transitively on the set of Weyl chambers. And this is not a coincidence. So first of all, I'll prove very easily that this normalizer plays a very important role in the theory of symmetric space of non-compact type, because it basically gives you a bridge between, at least a partial bridge, between the theory of like Weyl groups, which is a finite group, on the one hand, and isometries of your space on the other hand. So I claim that this normalizer and its action on A star, it preserves our root system. And moreover, it preserves it in the controllable way. So if you have K here, it maps the root alpha to some other root K alpha, and the corresponding root subspace GK alpha. In order to get it, you need to take the root subspace G alpha and act on it by the adjoint action of K. So the action of K on the root subspaces is kind of compatible with the action of K on the roots. That's the statement. The proof is very simple. So you take any vector in A and you take any vector in G alpha. Now here's what we need to compute. I want to show that K alpha is a root, and I want to show that the corresponding root subspace is just add K of G alpha. In order to, I'll show both of these statements in one go. In order to show that K alpha is a root, I need to find a vector such that the action of any H from my abelian subspace A, the action of this H, the Lie bracket of this H with this vector Y, is just the multiplication of Y by some number, and this number is precisely the value of K alpha on H. I wasn't able to do it like step by step because there was some problem with Beamer, so I'll just comment on each part of this computation. So you compute the Lie bracket of H, and then the adjoint of K applied to Y. Because the adjoint of K is a Lie algebra automorphism of G, it's the same as to apply add K to the whole Lie bracket, and then to write add K inverse of H. But now Y lies in the restricted root subspace corresponding to alpha. And add K inverse of H is some element of A. By definition, this Lie bracket is just Y times some number, and this number is the value of my root alpha on this vector add K inverse of H. And to the whole thing, I apply the adjoint of K. Now the adjoint of K is linear, so I can take this number out of the expression. So here I have this vector adjoint K of Y, and here I have this number. But remember, by definition of the action of this normalizer NKA on A star, if I have this contraction of this alpha, which is a functional on A, and add K inverse of H, which is a vector of A, it's the same as the contraction between K of alpha and H. This is basically just the definition of the action of K on A star. But now we've shown that if I act adjointly by H on this vector adjoint KY, it's the same as to multiply this vector adjoint KI by this number, K alpha of H. And this shows both that K dot alpha is a root and that the adjoint of K maps G alpha to GK alpha. Any questions here? Okay, and just to finish, so we've shown that this normalizer acts nicely on A star and preserves the root system. Now we actually can know something more. Because the inner product B theta on G is K invariant, the action of this normalizer on A star is not only preserves the root system, it is also orthogonal. It preserves the inner product on A star. In particular, together with this proposition on the previous page, it implies that this normalizer, it preserves the root data, it preserves the root numbers, the root integers. So for any two roots alpha and beta, you have this integer n alpha beta defined in this way. Because the action of K is orthogonal, it preserves these numbers. But by definition, orthogonal transformation, or rather just transformations of the space, of the ambient space of a root system, which preserve these numbers for any pair of roots, are called automorphisms of the root system. The group of automorphism of a root system is a finite group, and it contains the Weyl group as a normal subgroup. So basically, the automorphism group of delta is just the semi-direct product of the Weyl group and the automorphism group of the corresponding Dynkin diagram, which is just a very, very small finite group. So it turns out that the image of NK of this normalizer, not only it lies in the automorphism group, but it's precisely this Weyl subgroup, the Weyl group regarded as a subgroup of the automorphism group. And you can easily compute that the kernel of this representation is the centralizer of A and K. So you've realized your Weyl group as a quotient of this normalizer by this centralizer. And both of them are some subgroups in the isotropy. In particular, they are represented by isometries of your space. The proof that this is precisely the Weyl group is not very difficult, but I didn't have time, so I want to skip it. And I think this is it. Thanks for your attention.